Okay, so here finally we will finish off chapter 22. Okay, so this part we talk about the point charge in the electric field. So the equation is easy. At the very beginning, the definition is like E equals F over Q. So we just move this Q to the other side. It becomes F equals QE. So which means that after defining all the E field, so here we are comfortable to calculate the E field, at least for some simple structure. Okay, so now if we assume that in the area we have the E field, we know the E field at every point, and if we place a charged particle in the E field, then we will know, okay, there will be a force acting on the charged particle, which has the direction of the E field or opposite to it, depends on whether the charge is positive or negative. Okay, so here it just tells you the mechanism for the inkjet printer. Okay, so so let make it. Yeah, so let's try to explain it like this. So here you can see on the left side, it writes green, which means a green ink. So here we put the ink here, and then here we can add some charges. To the ink. How much charge we add to it is under control. There are some program behind to calculate how much charge we need to put on the ink, so that the ink can goes to somewhere we want. Okay, we try to shoot some ink from the left side, so there's some ink originally going to the right side horizontally with a uniform speed, because after shooting out there are no force acting on it. So according to Newton's law of motion, if there are no force acting on it, it should have a uniform velocity of movement. Okay, so after that we add the deflecting plate, which means the deflecting plate try to change the direction of the ink. Okay, so for the ink, okay, of course we try to put some negative charge there, and then we try to generate the E field pointing downward, which means that for the top plate we have plus charge, positive charge. On the bottom plate we have a negative charge. So we will assume that between this area, it will generate a uniform E field pointing downward. Okay, it will generate a uniform E field pointing downward. Okay, so in that case, it is a negative charge. So according to F equals QE. So Q is negative. So the force will be pointing upward. Okay, yeah. So in high school physics, we should have learned some similar movement like this. It's just like if you need to throw a ball to the right side, and then with the gravitational force mg, F equals mg, and then with initial velocity v, okay, it will flow like this in a parabola. Okay, so it is the other way around. If you just flip it upside down, then it is actually the same as this. But here, if we try to control control the charge amount, then we can try to control where the green dot, or maybe I change the color. Then we can control the green dot go to the which position of the paper. So by changing the charge amount, charge amount, we can control the position. Let's say X, that the inks go on the paper. So that's the simple mechanism of the inkjet printer. Okay, so let's see. We have a simple sample problem about this inkjet printer. Okay, so it says the deflecting plate of the inkjet printer with a superimposed coordinate axis, and ink drop with a mass of this one, very light, and a negative charge of Q to be capital Q, negative charge of negative Q, capital Q, enters the region between the plate, initially moving along the axis with a speed Vx. The length L of each plate is 1.6 centimeter. So this is L to be 1.6 centimeter. Okay, the plates are charged and thus produce electric field at all points between them. So we have a E field in this area. Assume the field is downward directed, uniform, and has magnitude of this value. What is the vertical deflection of the drop at the far edge of the plate? The gravitation, we assume that we should have a paper there. So that after going through this deflecting plate, okay, we can see where the drop goes. Okay, so here it says the gravitational force on the drop can be neglected. So as I mentioned in the previous chapter, the electromagnetic force is much stronger than the gravitational force. Okay, so try to calculate it here. So first of all, we need to calculate the time it takes from 0 to L, the time. So for the horizontal direction, there are no force acting on the ink. So on the x-axis, it is a uniform velocity movement. So the time t can be calculated as simple as L. T equals L over Vx, which is 1.6 centimeter. So be careful, centimeter is not an SI unit. So we need to change it to 0.016 meter. And then over Vx 18 meter per second. Okay, so this is 1 over 1125, or you can calculate the value as 8.89 times 10 to minus 4 second. Okay, just take this short period from the left side to the right side. Okay, so next we need to calculate the force QE. F equals QE. So Q is Q, or maybe I can use a capital Q. This Q is 1.5 times 10 to negative 13, and then times E is here. E is 1.4 times 10 to the 6th power. Okay, so this value is 2.1 times 10 to the negative 6 Newton. Okay, so this is the force acting on the ink in the vertical direction. Okay, so in high school physics, you should have known that y equals 1/2 at squared. Okay, so you should have known it. And according to the Newton's second law of motion, A is F over m. So we have F over 2m times t squared. Okay, so we just need to plug in the number. F is 2.1 times 10 to negative 7 here. And then over 2m. M is given here. So 2 times 1.3 times 10 to negative 10. And then times t is this one. 8.89 times 10 to minus 4 quantity square. So this value is nothing but 6.4 times 10 to minus 4 meter. Or you can write it as 0.64 millimeter. Or you can also write it as a 640 micrometer. Okay, so here I will just tell you, you need to remember some sort of so-called scientific prefix. Scientific prefix. Scientific prefix. Actually, I suppose you already know some of it. Just like giga is 10 to the 9th power. Mega is 10 to the 6th power. Kilo, small k, is 10 to the 3rd power. Okay. Of course, you also know C. C is less than 1. So C. So yeah, 1 is nothing. 1 is nothing. And then smaller than 1 is 10 to negative 2 centimeter is like 1 meter have 100 centimeter, so centi. But yeah, only meter will use centi. Other things won't use centi. So this is an special case. So other than that, we have a 10 to a negative 3rd power, which is milli. You still know that, millimeter, milliliter. And then even smaller, 10 to a negative 6 will be micro, which is a Greek letter. And then even smaller, we have a 10 to the negative 9, which is nano. Okay, this is giga. This is mega. This is kilo. This is milli. This is centi. Okay, and even smaller, we have 10 to negative 12, which is pico. And then 10 to minus 15 is the one you still need to know, is a femto. Okay, actually you don't really need to remember how they pronounce. You only need to know what are the scientific prefix for this value. These are the values. Okay, from 10 to negative 15 power to 10 to the 9th power, you need to remember. Of course, when you use the computer, usually you will face the giga, mega, kilo frequently. But for the smaller scientific prefix, then you need to somehow remember that. At least for milli, I suppose you know that in primary school. But for micro, nano, pico, and femto, then you need to remember it a bit, because it will occur in the sample problem or exam from time to time. So you need to remember a bit. Okay, so next, we talk about the dipole in an electric field. So here, we just try to put a dipole in the uniform E field. Just like on this graph, the E field is pointing to the right side, and we assume that it is uniform. Okay, so here, if we try to put the dipole somehow like this, with an angle between the E field and it, then it will start to oscillate, start to rotate and oscillate. Why will be like that? So we can consider here we have the E field pointing to the right side, and of course we have a positive charge and a negative charge with the same magnitude but opposite sign. Okay, so E field pointing to the right side. For the positive charge, F will point to the right side, which has the same direction as the E field. And for the negative side, negative charge, the force will have an opposite direction as the E field. So we have a negative F point to the left side. So in that case, you can consider this dipole is a fixed structure, and then a force dragging is bottom right to the right side, and then dragging is the top right to the right side, and then the bottom left to the left side. So it will make the dipole rotate in the clockwise direction. Rotate in a clockwise direction. Clockwise 顺时钟，或者顺时针，或者顺时钟，广东话叫顺时钟。Okay. Or counterclockwise is 逆时钟或者逆时针。Okay. So in this case, it is clockwise. Okay, but if the E field is like this, so it will start to rotate clockwise, and sometimes later it will rotate horizontally. But at that time, it won't have any force acting on it, but there will be some kinetic energy. So we will keep rotating forward until the dipole rotating to this angle. So all the kinetic energy or the angular momentum, angular kinetic energy will change to the potential energy, and then it will swing back. So if we place a dipole in the electric field, it will oscillate. If the initial angle is not the same as the E field direction, it will just oscillate there. Okay, so in that case, we can quantify it to be the torque 力矩 of an electric dipole. So to be P is of course this one. The dipole moment cross the E field. So I suppose you know how to do the cross product, but at least I can somehow show you that you use your forefinger pointing to this direction, and then you try to rotate to the E field. Then your thumb will pointing into the page. This cross means the torque is pointing into the page. If it is something like this is out of the page. Okay. So so it means that the torque is pointing into the page, and according to the right hand rule, okay, your thumb pointing into the page, it rotates according to the direction of your forefinger, so it is rotating clockwise. Okay, so for the cross product, it is like PE sine theta. So for the electrostatics, we don't face this cross product so much. So for the magnetism, for the second half of this semester, we will talk about the cross product more frequently. Okay, and the next part is the potential energy. The potential energy will be negative P dot E. Negative P dot E. So which means that if P and E points to the same direction, it will have the, this value will be the maximized, and which means that with the negative side, U will be the minimum size, which means that if P and E points to the same direction, then U is minimized. Of course, this minimized value is not zero, but potential energy is a relative concept, just like if it is a floor, for the gravitational potential energy, it is like, if this is U is 0 and this is H, so this is like U equals mgh. And if you define the U at the floor is not 0, then the U for the upper one will just add that value accordingly. So because usually when we consider the potential energy, we will consider the potential difference, so it doesn't really matter what the exact value is. Okay, so at least we know that it is a minimized value. So it's just like we have a curvature. If we just roll a ball, it will just go down and go up. So at this point, we have the minimum potential energy, but the maximized kinetic energy. So as this case. Okay, so just go a bit about this one, because you are civil engineer student, you should be familiar with the mechanics stuff. Okay, so here we have an additional sample problem, to finish off this chapter. Okay, so this one, here it says we have a clock face has a negative point charge from negative Q to negative Chap Q fixed at the position, according to the numerals. Okay, which means that we have something like, this is a clock face. Of course, for a clock face, we have some number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or something like this. Okay, let me try to copy this one. No problem. Okay, so it means that at 1 it has a negative Q, negative 2Q, so on and so forth. Up to here we have a negative Chap Q. I don't write it one by one. Okay, so it asks you the clock face, the clock hands do not perturb the net field due to the point charge. At what time does the hour hand point in the same direction as the net as the E field vector at the center of the dial? So we would like to find what is the E field direction at the center. Okay, so we can also familiar with the how to do the cancellation. So which means that suppose we have a negative Q at 1. And then we have a negative 7Q at 7, which means that at this point it will generate E field pointing to this side with proportional to 1, and then we will have a E field generated by the negative 7Q, which is proportional to 7 of something. Okay, so in that case, 1 and 7 can be partially cancelled. It turns out to be 6, or you can regard it as we cancel the charge, negative Q and negative 7Q to be negative 6Q, like this. Okay, and this kind of cancellation can be repeated, like if we have this negative 2Q, this is negative 8Q. Okay, we can also do the cancellation. We cancel this negative 2q with this negative 8q to be negative 6q, also negative 6q. So this one points to this direction, this one points to this direction. And 3 and 9 will also can cancel negative 6q. 4 and 10, 5 and 11, 6 and 12. So after the cancellation, we altogether have six forces, pointing to 7 o'clock, 8 o'clock up to 12 o'clock. All of them cancel down to be negative 6q, negative 6q, negative 6q, negative 6q, which means that all the E field here have the same magnitude. Okay, so finally, what is the direction of the overall E field? So it will be simple because the force will have the symmetrical axis somehow between 9 o'clock and 10 o'clock, which means that at what time? Which means that 9:30, the clock, the hour hand will point to the 9:30, which is right between 9 o'clock and 10 o'clock, which has the same direction as the E field at the center. Okay, so this is a simple one. And then next, we have another sample problem. Okay, so it asks you, suppose you design a apparatus with a uniform charge disk of radius r to produce an E field. Okay, the field magnitude is most important along the central perpendicular axis, which means the C axis here. Okay, at point P, distance 2r. Okay, it tells you that the radius is capital R, and the distance from the center to the point P is 2r. So as this one, 2r. Okay, so cost analysis suggests you to switch to a ring of the same outer radius r, but with inner radius r/2. Okay, so we try to cut some of it. Okay, so this is r/2. In terms of area, of course, this is not half, but in terms of the radius, it is half of a circle. Okay, assume that the ring will have the same surface charge density as the original disk. Okay, so which means that this is sigma, this is also sigma, but the area are different, so that the total charge amount of this disk and on this hollow disk is not the same. The total charge amount are not the same. Okay, so assume that the ring will have the same surface charge density as the original one. If you switch to the ring, by what percentage you decrease the electric field magnitude at P? Okay, so first of all, we can try to this one is A, this one is B. Okay, so let's calculate EA. EA will be sigma over 2 epsilon naught, and then 1 minus actually we need to make use of E equals sigma over 2 epsilon naught 1 minus Z over square root of C square plus capital R square, because this R this Z is not much larger than capital R, so that we cannot ignore the second term in this case, so we still need to keep it. Okay, for this one, Z equals 2R, which means that this is 2R, this is 2R quantity square, and then plus R square, and then take the square root. Okay, so this one is like sigma over 2 epsilon naught, and then 1 minus 2 over square root of 5. Okay, because all the R can be cancelled. And then for the second case, rather than calculating the ring, we calculating the inner part. We can calculating the E field generated by the inner part, and then we subtract it. Then it will be the value generated by the ring. Okay, so here we try to calculate E hollow 空心的 okay, so it will be sigma over 2 epsilon naught, and then 1 minus, still z equals 2r, so we have 2r here, we have also 2r here, but for the hollow part the radius is only r over 2, so we have r over 2 quantity square. So this value is sigma over 2 epsilon naught, and then 1 minus 4 over square root of 7. Okay, so this is just some algebraic calculation. Okay, so finally, if we need to calculate how much E field is decreased, how much percentage is decreased, so we can have a E hollow over EA. So it is so for the first part it will be cancelled, so it becomes 1 minus 4 over square root of 7, and then all over 1 minus 2 over square root of 5, and then we can multiply it by 100%. So final answer is 28.3%. 28.3% for this sample problem. Okay, so here we have conclude this chapter.